Hi, today we're starting Momentum. And for Momentum, we are going to start talking first about center of mass. And we want to talk about center of mass. For center of mass, we look at the mass, and it acts as if the mass, all the mass of an object or a system is located at its center. And so what that does is that helps to reduce some things for us, to kind of simplify things. If we treat the entire mass of an object or a group of objects that's acting as a system, and treat it as a point mass, it can really simplify some things for us. And we can talk about where we would balance it, where it would spin. This is where it would spin about his center of mass, because when we talk about angular momentum, that's going to be important. And so if we talk about a meter stick, we have a meter stick. Its center of mass is located at the center. This is a meter stick. It's 1 meter long. And the center of mass will be like 0.5 meters away from the end. Okay, but we probably won't see an object like that. We will probably see a more complicated object or a system of objects. So if we have a system of objects, could we find the center of mass for that system? And so let's look at this system of objects. I'm going to draw a reference out here. So we have mass 1, we have mass 2, and we have mass 3. And mass 1 is located at 0 meters, mass 2 is located at 2 meters out, and mass 3 is located at 3 meters out. And if we wanted to figure out where is the center of mass for this whole system, we could use this equation to figure it out. And it is center of mass, the position of the center of mass is equal to mass 1 times position 1 plus mass 2 times position 2 plus mass 3 times position 3. And if we put all of that over mass 1 plus mass 2 plus mass 3, we could find the center of mass for this system right here. And so let's go ahead and do that. Let's find the center of mass for this system. And so if we look at this system, if we look at mass 1, let's give masses also. Mass 1 is 1 kilogram. Mass 2 we'll say is 2 kilograms, and mass 3 will be 3 kilograms. And so if we go down here and we're talking about what is the mass of object 1? It's 1 kilogram. What is the position of object 1? And it's at 0 meters. So we add that to object 2. Object 2 has a mass of 2 kilograms and a position of 2 meters. And then object 3 has a mass of 3 kilograms, and it is located at 3 meters out. And we divide that by the mass of mass 1 plus mass 2 plus mass 3. And so we get, when we multiply everything, we have 0 plus 4 plus 9, which gives us 13 over 6, which gives us a center of mass at approximately 2.2 meters. And so if we look at our system up here, our center of mass is somewhere over at 2.2 meters. And so we could treat this whole system as a point mass at exactly 2.2 meters. And this is where, if this group of objects spun together, it would spin on its axis about the system. It would balance right there. So looking at that, if we took our same meter stick as before, and our center mass is still right at the 50 centimeter mark. And let's say that instead of balancing it there, we actually hung a mass right here. Now we can treat this as a center of mass of this system, the center of mass from the mass of this system, and we could use this to find where its balancing point would be, and it would be somewhere in between these two. Okay, but you might also have to do this for something in 2 dimensions. And so let's just say we have a system set up and we have four masses. We have our four masses set up, and this is mass 1. And mass 1 is 2 kilograms. Here's mass 2, and mass 2 is also 2 kilograms. We have mass 3 over here, but mass 3, we're going to say mass 3 is 4 kilograms. And over here, mass 4 is, and we're going to give that one also 2 kilograms. Okay, so they're not all the same mass, and we want to find the center of mass of this system. And so if we look at this, if we know the location, and let's just say that this corresponds to a y value of 1, and this is 0, this is 0, and this is 1. We can find the center of this system, and as you might suspect, we would need to break up the horizontal components and the vertical component of each of those masses. And so we would have to find the center of mass of the horizontal component, and then we want to find the center of mass of the y component. So let's start with the horizontal component, the x component. And so we would do those separately. If we look at the x, if we look at mass 1 has a mass of 2 kilograms. But if we look at its location on that x-axis, it's at 0. And then if we look at mass 2 also has a mass of 2 kilograms. But on the x-axis, if we look at its position in the x, it's also at 0. So let's go over to mass 3 is 4 kilograms. But mass 3 is at 1 meter out. And then our last one, and let me slide these over to get a little more room. Okay, and so if we do our last mass 4, we have a mass of 2 kilograms, and that is at a position of also at 1 meter. And so if we take that and divide by the mass of mass 1 plus mass 2 plus mass 3 mass 4, we get 2 plus 2 plus 4 plus 2. And so when we do that, we have, if we look at this, we have a total of, this is the first one is 0, 0, 4, and 2. So we have a total of 6 in the numerator. And on the bottom, when we add all of those up, we have 10 meters. And so when we look at this, we have a position of 0.6 meters for our horizontal center mass. So let's go down now and let's do our vertical center of mass. So if we look at that, vertically, if we look at the first mass, it has a mass of 2 kilograms, 0, position of 0. The second mass also has a 2 kilogram mass, but it's at 1 meter on the y-axis. And if we look at the next one, mass number 3, mass of 4, a position of 1, and then the last one has a mass of 2, but a position of 0 on the y-axis. And so if we look at that, if we add up all the masses, like we did before, 2 plus 2 plus 4 plus 2, we get a total of 10. When we look at the top and add those up, we have 0 plus 2 plus 4 plus 0. So we have 6 over 10 again, or 0.6 equals our center mass in the y-axis. And so if we go back to our grid and we come over here at approximately 0.6 and 0.6, the center of our mass is right about there. It's a little high. Okay. So most of the time you can do this by inspection. Hopefully you could look at this and tell it should be a little bit up and to the right of the middle, but sometimes you have to calculate it. So now let's talk about center mass of velocity. And so if we look at a 1 kilogram object, and it is moving to the right, and it has a velocity of 2 meters per second, and we look at a 2 kilogram mass moving to the left, and this has a velocity of 1 meter per second. We can't look at the center of mass for the object because the objects are moving. But if we take it and we look at this whole system, we can find the center of mass of the system. And so if we look at center of mass, we would have mass of the first object times the position of the first object plus mass of the second object times the position of the second object divided by the mass of the first object plus the mass of the second object. So this is what we said before. But if we want to look at the velocity of the system, we could take the position of the center of the mass and see how it changes over time. And if we divide this by time, we could get the change in velocity, or the center of mass of the system. And so then we get, when we do this, we get velocity of the center of mass equals m1 v1. If we divide this position by the time, and then we get m2 divided by, or times v2 when we divide its position by the time. And all of that over m1 plus m2. And so this would be how we would find the center of mass of the system. And if we look up here, if this is moving 2 meters per second to the right, and this is moving 1 meter per second to the left, the center of mass of the system is moving to the right, and we could figure out how fast if we wanted to, and we could get the center of mass because the velocity of an object remains constant unless there's some kind of net outside force acting on it, and we know this because of Newton's first law. And if we look at that, the same holds true for a system. For example, if there's no outside force, you can't do something like lift yourself up. It has to come from an outside force. And so this system would continue to move to the right. Okay. Um, this also holds true when the velocity is 0. And so let's do one more example. So let's look at, we have a boat. We have a boat, and here's a dock. And I will label it dock since it doesn't really look like a dock. But on our boat, we have someone standing on this end. And if we look at that boat, the boat has a center mass. The boat is about 5 meters long, and the center of mass is in the middle, about 2.5 meters from the edge of the boat. And the boy's standing on the opposite side, and the boy has a mass of 50 kilograms, sorry, which is around 120 pounds, 120 pound kid. And so if we're looking at him, we could find the center of mass of this system. And so let's look at the boy standing on the boat, the center of mass of the boy in the boat. And so if we look at that, we have, let's find the center of mass for that system. And so let's start with the boy. The boy has a mass of 50 kilograms, and the boy is standing 5 meters away. He's standing on the edge of the boat. Now, if we look at the boat, now I need to give you a mass for the boat. This boat has a mass of 100 kilograms. And so the boat is about twice as heavy as the boy. And so if the boat has a mass of 100 kilograms, and its position of its center of mass is at 2.5 meters, divide by the mass of the boy plus the mass of the boat. We end up getting, we have 5 times 50 is 250 plus 100 times 2.5, we get 500 over 150. And so we have 3.3 meters is the center mass of our system. And so this is going to remain the center of mass. So if we have another situation where, you know, we still have our dock, except the boy starts walking. And so the boy starts walking this way toward the dock. We know that the velocity of the center of mass is going to stay the same. The velocity of the center mass of the system is 0. And the location of the center of mass of this system is going to remain the same. And we found out that it's at 3.3 meters, so right about here somewhere is the center mass of our system. And the center of mass of our system is, if we calculate it, it's about 0.83 meters away from the center of mass of the boat. And so if we walk over here and we have the situation where now the boy walks from that end of the boat to the other end of the boat, the center of mass of our system is going to remain at the same spot. Center mass of our system is going to remain at 3.3 meters, and the center of mass of the boat will be about here. This would still be about 0.83 meters away from the center mass of the boat, so that would all be the same. We'll go ahead and stop there and continue next time.